All right, hello everybody. This lesson here, we're talking about the speed of sound in air. We're going to look at how we know what the speed of sound in air is, what it's based on, and then things related to it like Mach numbers for aircraft traveling fast speeds, echolocation, and sonar uses as well. So as usual, the questions are there for you at the start, and here we go. So speed of sound in air, this is kind of a graphic, it'd be like the police officer radaring the speed of sound as a little joke or whatever. But we know the speed of a wave is determined by the characteristics of the material it's traveling through. So since sound is a wave traveling through air, then we would look at speed, the characteristics of the air itself. I said normally through air, it can travel through other materials like water and steel and things like that. Any material really. Sound waves can travel through the ground even. Excuse me. So things like the pressure would be related to think of this like tension almost. Temperature would have a big effect. Humidity, density, density might be related to humidity and so on. Turns out that these factors, what the biggest effect is temperature, and so that's the main one needed for determining the speed of sound. This equation gives the speed of sound based on temperature. It's in meters per second. So we have a base value of 331 at 0 degrees Celsius. For each degree Celsius increase, you're adding 0.59. And that's the equation that represents the speed. I'll talk a little bit more about that in just a second. So, the higher temperature makes sense because the molecules are moving faster. The air also becomes less dense. If you think of the vibration of the molecules being faster, you could picture the transfer going faster from one molecule to the next. That's just a way to try and reason it out and think like, oh yeah, it kind of makes sense, but just know to use the equation. So where does that equation come from? Well, if you think about if just taking measurements, it really just comes from experimental data. So if you look at the format of that equation, it's really like mx plus b, right? So picture an experiment where a bunch of speeds were measured at different temperatures, and then you just plot it, and you end up finding it has a y-intercept of 331 and has a slope of 0.59, and bing bang boom, grade 9 math, you've got yourself an equation for the speed of a wave based on the temperature. Okay, so that's definitely a cross-curricular link, if you will, the grade 9 math stuff. If we did a bunch of measurements like that, the math analysis would just be grade 9 level. So I know a lot of people say that a lot of math and physics, but grade 9 level math in a grade 11 course shouldn't be too much of an issue, right? It's actually one of the kind of downfalls of the universe itself, is that the math that's necessary to describe and understand everything is exceedingly complicated. The more you get the highest level of string theory, trying to describe all the equations in the universe you might have heard about. Keeping on going here, though, using that equation is fairly simple. You just look at your given information. You're looking for the speed based on the temperatures, so you just analyze and say, okay, well, I've got an equation that is based on that, and you just plug in the temperature and calculate the speed. Okay. In this case, if we're looking at correct significant digits, I think we had 3, 3, and only 2, right? So from the multiplication here, we'd really only have 2. When you're adding, really we'd only have like 1 decimal place. There's multiple things to consider, but in the end, 2 significant digits. So basically approximately 350, or is what you'd round this to, right? So 3.5 times 10 to the 2 would be the way to show this so that the number of significant digits is obvious. But if you said approximately 350, that would be sort of sufficient as well, kind of communicating with words. Another version of this, if you were given the speed, then you could actually calculate what the temperature must have been. So if we calculate the speed to be 360 meters per second, we could plug the 360 in for the speed, subtract, and then divide all the math steps to solve for the temperature and find that it's 49.15 degrees Celsius. So it would have been a fairly hot room, I guess, for that speed. Okay. So working with the equations, that's like these questions here, 1 and 2, just parts A and C, because you don't need to do 4 of them. Just do 1 for practice with help, and then with 1, the next one, if you can do it without help from the lesson, then you're good to go. If not, practice some more, of course, until you're able to do it on your own. Next step was Mach number. So Mach number is to do with how fast a plane is going as a multiple of the speed of sound. So Mach 3 is plane traveling at 3 times the speed of sound. So the formula for it is pretty simple, where the Mach number is just the speed of the plane, just the speed you're talking about divided by the speed of the sound at that place and time and temperature and so on. So use the speed of the object. S, subscript S, is the speed of sound. So Mach 3 means 3 times the speed of sound. So, in the previous example, we had 346.6. So Mach 3 would be on 1039.8 meters per second. Okay. So it does depend on the temperature. Okay. Mach 3 doesn't always mean the same thing. If it was 12 degrees, then you'd have to calculate the speed at 12 degrees and then multiply that by 3 and get, Mach 3 in that scenario would be 1014.2. So that's how Mach numbers work. And then the last thing is to do with echolocation. Obviously, once you're calculating speed of sound and so on, you could calculate how long it takes to go there and back. And so, echolocation wise, we could look at how long the echo takes to come back from a dolphin or whatever, or a bat or whatever is using echolocation. And so you could do calculations, of course, right? So we'd have the speed of the sound in the water and be able to use the time interval to get how long it takes to go one way. So that one there, 0.1 seconds is there and back. And so, of course, you have to divide that by 2 to get the distance the fish are away. And that's obviously like how a depth sounder would work, right? It would calculate out the depth of the fish and then be able to put a graphic on the screen showing where the fish are. Bats do a very similar thing, of course. Depth sounders, fish finders, and so on. Picture the sensor just making a little sound and then listening for the echo of it, timing how long it took, and so on. So I have a little clip here that I'm hoping won't ding me for copyright stuff. I'll find it here. So I'll play a brief bit of it. I probably can get away with it. So in Finding Dory, the whale, I forget the name. It's been a long time for me. But the whale uses echolocation, right, to find. Basically, there's a clip I was looking for. I couldn't find it, but basically found the truck. Saw the truck was driving away with the whales in the back or something like that. I forget maybe I'm thinking of the wrong movie, but I did find this clip. So I want to show you the idea that people don't really think of, but that you can actually get a visual from this. There's no reason why not, right? We get a visual from light entering your eyes. It's basically thought that bats and whales and so on get a visual picture using echolocation as well. And so it's just your brain, your brain getting an image based on the echolocation. Hopefully that's not a copyright infringement here. So that's a little bit more work there. Maybe, 1, 2, 3, 4, 5. It's reasonable, I think, based on a grade 11 level. Let me know if this one takes a little longer. I might. These are all pretty quick, right? Mach number 385 would just be like in standard air conditions. So basically, do the speed of sound divided into that, right? So divide by 331 or something, whatever. Just don't make a big deal of it. Anyways, let's leave it at that. And hope you're doing well. Let me know if you need anything. All right. Bye for now.